Okay, let's think about adiabatic heating and cooling by sudden compression and expansion, first observed in the 1750s and widely thought about or appearing in the literature by 1779, and what that means for Newton's speed of sound measurement. The next character in our story is Pierre-Simon Laplace, the French scientist. Now, in 1802, he suggested that the heating by compressing the air might account for the 20% error in Newton's theoretical value for the speed of sound. So what I'm going to do is I'm going to clap my hands. Now, what happens, of course, is that the energy of my clapping hands set off a sound wave through the air, and that sound wave traveled through the air to the microphone on my computer. So let's look at that transfer of energy through the air. Now, Dalton had published on the atomic theory by now and about adiabatic phenomena, and scientists began to wonder if this adiabatic phenomena thing could be applied to the theoretical problem of the speed of sound in air. And could that then be related to the specific heat ratio of gases, or in this case, the specific heat ratio of air? Now, Laplace realized that when the sound wave compressed, the air particles, or the air molecules, they would get hot. Then, as the sound wave traveled through the air and the particles were no longer being compressed, they would rarefy or become farther apart, and they would cool down. And then the energy of the sound wave would compress some more air particles, and they would get hot. And then as the sound wave passed through the air particles or the air molecules would cool down. As the sound wave went to compress the next set of air molecules or air particles, they would get hot and then cool down. So when we're talking about longitudinal waves like a sound wave, compression is merely that region of the wave where the particles are closest together, and rarefication is the region where they are farthest apart. So actually, let me move this particle apart a little bit. Okay. And the particles are farthest apart where the air is rarefied. All right. Oops. Now, the important thing to remember about this is that we had a theoretical model of understanding temperature and pressure, and that was called Boyle's law, which was in 1662. Now, in 1662, Boyle stated that the pressure of a gas times its volume is going to equal some constant, but this law only applied at constant temperature. So, pressure times volume equals some constant at a constant temperature. But when we are dealing with a sound wave, we are not dealing with a constant temperature. We're dealing with hot, then cold, then hot, then cold. So Boyle's law is not going to apply when we're trying to figure out the speed of sound. Now, I just want to mention that Boyle's law was also discovered by the French physicist Edmond Mariotte in 1676. So if you studied chemistry in France, you might know Boyle's law as Mariotte's law. All right, now before we move on, let's talk about a little bit where we are. So this is another spoiler alert. We know today that the speed of sound in a gas depends on its adiabatic compressibility. All right, so what does that mean? That's a fancy way of saying adiabatic, no transfer of heat. And compressibility is a function of the gas pressure, as the compressibility will increase as the pressure decreases, which kind of makes sense because if you have gas at a very low pressure, you're able to compress it. If you have gas that is already at a very high pressure, you're not going to be able to compress it much more. So if we're going to think about the adiabatic compressibility of heat, we can say the compressibility is 1 divided by the pressure. Did I just say the compressibility of heat? No. When we're going to talk about the compressibility of a gas, it is given as 1 divided by the gas pressure. And since we are working in the real world and dealing with non-ideal gases, we often apply a correction factor for a non-ideal gas. So compressibility, adiabatic compressibility. Remember, Laplace was thinking about adiabatic compressibility when he thought that there were regions in that sound wave or sound waves that were hot and cold and hot and cold. The ability of the energy of the sound to compress the gas. Then the release of heat as the gas expanded, the ability of the sound wave to compress the gas, and then the release of heat when the gas expanded. So the adiabatic compressibility can be determined by the heat capacity at constant volume, heat capacity at constant pressure ratio. So if we're going to determine the speed of sound in air, we need to think about the adiabatic compressibility of the air, and we can determine that by the CV and CP ratio. Now, we're almost at the point where we are going to talk about the experiment that gave us a way to measure the heat capacity at constant pressure versus heat capacity at constant volume ratio. So while you're thinking about that, I'm going to stop the recording and resume with part 3.